All right, well, welcome everybody. So today we're going to be talking about two concepts here, which I see as very interrelated with each other. First is talking about the natural modes of a string. The second part I want to say is also and harmonics is the other part. So let's see here. Maybe what I'll do is like this: harmonics and natural modes of a string, or standing waves. Okay, so the reading is chapter 4 and chapter 8. These two go together. But first, let's just practice. This is a good review question for us. If a tuning fork vibrates steadily at 344 hertz, what is the physical distance in the room between one high-pressure peak and the next one at any given moment in time? I'd like for you to stop and work this one out. Okay, and we're back. If you assume room temperature here, we can assume that the speed of sound is 344 meters per second. Our wave equation that we can use, this is our one of our most important equations of our class, is figuring out that the length of the wave that we're interested in other words, the distance between one high pressure place and the next, is going to be V over F. And so that's really what we're trying to figure out. Is it says physical distance between one high pressure peak and the next one, but really what I'm wanting for you to get out of this kind of question is realizing that, well, this is the length of a wave, which is lambda. So the length of the wave then is just simply the speed of sound divided by the frequency. And of course the frequency is in 1 over seconds, or inverse seconds, and yielding you a result which is 1 meter. So I chose the numbers to make it a little easier for the math to work out on this one. This is just to help remind you and reinforce an important concept in this class. So that is a sound wave that's propagating through space. I drew sort of this channel just to kind of simplify the story so it doesn't feel like it's too complicated. And of course sound waves propagate out in all directions, but if you have a little channel you could just sort of almost capture a little shot of kind of from left to right, what this motion looks like. So we've talked a little bit about, we've had some experiences now with a wave on a rope. And this video here, I'm going to open this up here, talking about a wave. Please watch this video.
This is a demonstration of wave speed on a rope. The wave speed depends on the tension in the rope in an inverse relation, well, in a direct relationship, actually. So if we don't have much tension in the rope, the wave speed is fairly slow. But as we increase the tension in the rope, the speed increases, and then at higher tensions and yet higher tensions, the speed gets very high. So the little piece of tape in the middle of the rope actually helps you to visualize the amplitude of the motion as the rope comes up, comes back to its equilibrium position, and then down, and then back to its equilibrium position. This piece of tape indicates the amplitude, the distance from the equilibrium position, either to the positive point or the negative point. Bottom line is that the wave speed is slow for low tension, high for high tension. And that's important for tuning your violin strings or your piano strings. You're going to increase the tension, increase the wave speed, increase the frequency at which the string vibrates.
Okay, so hopefully you caught all that. I think it's good to review some of the things that we might have been sinking in, but in other words, that the important point is that if you increase the tension, you increase the speed of the wave. So in other words, the time that it's going to take for that wave to hit a wall and to reflect back, that time is going to take less. So now, what happens when a wave hits a wall and then returns? Well, one of the things that happens is that it interferes with itself. Or, well, you could also think of it as that if you sent in successive waves, one after the other, then the ones that are reflecting are going to be interfering or adding with the ones that are returning. So I'd like for you to watch these videos. I'm going to let you watch the link on the bottom, the standing wave video, and then I'm going to show you instead the more boring version. And I'd like for you please to watch this because it'll give you a little bit more perspective on how waves are moving and adding with each other. But anyway, here we go with more boring version. What you're looking at here is two different waves. It's still trying to figure out how to maximize here. Just a second. Okay, there we go. What you're looking at is one wave that's going to the right, one wave that's going to the left, and the thing at the top is the addition of the two. You can perhaps convince yourself of this because right now these two waves are lined up with each other, the y1 and the y2, and you can notice that this one's number 1, this one's at 1, and so this one is going to be at 2, the addition of the two. However, when they move, now you can see that when this one is at a maximum, when this one is at a minimum, the y1, then y2, the blue one, is at a maximum, just about. And so they actually end up, this one subtracts with this one, and they almost cancel out. And so if I get it just right, there we go. If I get it just right, I can actually see that when a maximum hits a minimum, that they're actually canceling out, and we can see that it's almost zero. So in other words, this falls into the category that waves just add with each other. Okay, so we can create these standing wave patterns. And so the thing I want to maybe mention to you, which is interesting, is that even though there's waves like going left and going right, it looks like it's just staying there. And so if you looked at any one particular point, you could say, well, it's just going up and down, and this is called a standing wave. So the standing waves look like this. It's kind of a pictorial demonstration. There's actually many what are called modes or natural modes of vibration. This very top one here, you can imagine you could have a string tied on one side and tied onto the other, for example, of a guitar. And when you pluck it, it moves back and forth and back and forth. And that's what we're looking at here. And then the lowest mode, we'll give some names to these in a second, is going to just be the string itself vibrating up and down and up and down. It turns out that's not the only way that a string can vibrate. You can also vibrate it so that there's up and down on this side, up and down on this side, but in the center it's not actually vibrating at all. Similarly, if we kept going, we could see that there's some vibration here, here, and here, but not at these two places in the center, and so on and so on. And so we call these as harmonics. This is going to be the first harmonic. This will be called as the second harmonic. And you can notice actually that it acts as if it was just a string with half the length. And maybe if you're thinking about this, you might notice, well, if that's true, if it has half the length, maybe its wavelength is half as much, and that must mean twice the amount of frequency. So this is called the second, third harmonic, fourth harmonic, fifth harmonic. And the way you can figure out which harmonic it is very simple. You just look to see how many lobes there are. So if there's 3 lobes, it's the third harmonic. If there's 4 lobes, it's the fourth harmonic, etc. The interesting thing also, and you'll see this in chapter 8 in the book, is that, as well as chapter 4, so page 43, page 84, you'll see that the second harmonic has twice the frequency of the fundamental. The third harmonic has 3 times the frequency of the fundamental. So, for example, if the first harmonic was 100 hertz, then the second harmonic would be 200 hertz. Third harmonic would be 300 hertz, etc. Let's try an example to test our understanding. If the frequency of the first harmonic is 110 hertz, what is the frequency of the third harmonic? Go ahead and pause here and check to see which one you think it is. Okay, we're back, and hopefully you saw that if the third harmonic is just 3 times the fundamental frequency, then that should be 3 times 110 or 330 hertz. Let's try another example here. Which harmonic is 1 octave above the fundamental? Well, the fundamental is also called as the first harmonic. Go ahead and pause here, and hopefully you remember that the octave means means multiplied by 2, the frequency. Okay, so if you remember that going up an octave means multiplying by 2, the frequency, then you will find that it is indeed the answer is the second harmonic, which is going to be the second one that's shown here. So the answer would be A in this case. Okay. So here's something that doesn't have to do with a string instrument, but it does have to do with harmonics. A bassoon has a third harmonic of 600 hertz. So what's the frequency of the fifth harmonic? So this might require just a moment to remember what you know about harmonics. If you know the third harmonic, can you figure out the first? Go ahead and pause here and see if you can work this one out. All right, we're back. So hopefully you figured out that if the third harmonic is 600 hertz, that means that the fundamental, right, is going to be 200 hertz. So now that you have the fundamental, you can figure out any of the harmonics, and the frequency of the fifth harmonic should just be 5 times the fundamental. Now I'm going to just bring my my sketch pad here just to work that one out. So if F3 is equal to 600 hertz, that's equal to 3 times the fundamental frequency. So if that's true, the fundamental frequency is 600 divided by 3, or in other words, 200 hertz. Now that I have the fundamental, I can say, well, I want F5. Well, F5 is just 5 times the fundamental frequency. In other words, that's 5 times 200 hertz, which is equal to 1,000 hertz, or you could also write it as 1 kilohertz. That's also okay. Good. Going back to the slides, we can find that the answer indeed is D, 1,000 hertz. So waves just add up with each other, and one way that we can see that here is if we have a plus and a minus and a plus and a minus, if we add that to this other one that goes plus and minus, we'll see that it makes a rather complex waveform. And in fact, if we wanted to make something that looks like a slope and then goes up and then the slope then goes up, we'd have to add up all the right sinusoidal waves in just the right way in order to get that. And so we could imagine that if we summed up all of these different sinusoidal waves in the right way, we could actually make something that looks like this. So the sum of these pure tones, in other words, pure sinusoidal waves, gives us a complex waveform. And so this actually creates the timbre, or the unique quality of a steady tone. And I'll just briefly go to the simulation here, just so we can kind of see what this looks like here. This is a simulation that allows us to explore additions of different types of pure waves. Okay, still opening that here. Okay, so it's opening now, and once that is finished opening, I will make some comments about that. Okay, here it is. Good. So you can see here that I have one single sinusoidal wave. I can show multiple oscillations of this thing. For example, if I set the amplitude to 0, I can go to the next one and make a different frequency, or I can make a higher frequency. That's yellow, it's probably hard to see. This one here, green. So you can see that each one has its own frequency, and at the bottom you see a sum. Well, the sum has basically just so far been tracking what these different harmonics are. But for example, if I add the first harmonic to the green harmonic here, you can actually see that it's, or let's try even this one, this higher one here, this purple one. You can actually see that it's like I have the sum looks just like the red wave, but it has these little ripples on top of it. That's because those little ripples added and subtracted, and so it made it look kind of like a, I guess you could call it like as a crappy sine wave, right? That it kind of like, it looks like a sinusoidal oscillation, but it's not really quite that. So in other words, I can pick these guys with either negative or positive amplitudes, and I can make all kinds of unusual looking waveforms by doing this. And in fact, if I pick something like a triangle wave, it's called a triangle because you can actually kind of see here that it looks like a triangle going up and down and up and down. That is what you get when you add these different waves with just the right amplitudes. Or if I have a sawtooth wave, it's just the right amplitudes of these things all added together. And another one that's interesting is a square wave. If I add this plus this plus this plus this, notice these are all odd harmonics in a 1, 3, 5, 7. And I can get something that looks like flat top and then a flat top on the bottom and a flat top on the top. And this is called as a square wave because it looks sort of like a square. So we can also listen to what these sound like. So this is a square wave. This is a triangle wave. This is a sawtooth wave. And this is a pure sinusoidal wave. So you can kind of get a sense for what these sound like. The pure sine wave is the one that's the most pure. That sentence didn't really make a lot of sense. And maybe you can feel that it doesn't have a lot of complication to it just in the way that it sounds. Whereas, for example, a square wave, it feels like a harsher wave. So it depends on how you interpret the sound. Okay, so we'll go back here, and I'll say that if we record sounds, for example, as is done in this program called Audacity, you can see that this is the recording of a bird chirping. So this is, for example, this bird here. So as we listen to that kind of sound, we can notice that the recording of it shows, the waveform shows the pressure variation with time, and you can see the wah, 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 these three calls that this bird makes. And then you can also see in the spectrogram there's actually quite a lot of complex information in there. There's many frequencies that are all adding together, similar to the simulation that we just looked at. And that is what is ultimately responsible for the fingerprint or for the special or unique type of sound that bird is creating. And so you can also look at a slice. So for example, slicing through this 4.6 seconds, you can see that the spectrum looks like this and has several bumps. If you were to turn this on its side, you could actually correlate those bumps to these particular lines across here that all make up the frequency content of this bird's chirp. So now we're going to move on to talking about a specific way that we can create harmonics, which is by creating standing waves on a string. And so these standing waves will have nodes and antinodes. And so imagine a string bouncing up and down. And we can create these different modes, as was shown in the video earlier, where there's certain places along the string that don't actually vibrate up and down, and that some that do. So we'll call the nodes as the places that don't vibrate up and down, and the antinodes, or sometimes you'll hear me call them as the lobes, because they look like earlobes or something like that, and the ones that are vibrating back and forth. So this is our equation here that you can find in Chapter 8. And you can notice that where this comes from is, and I'm going to just cut to the video, or to the camera in just a second here, and just show you that this is our equation. This is something that should go down on your crib sheet for the exams. We have tension, and then we have mass per unit length, and then we have the length of the string. And all these put together will give us our frequency. So cutting to the video, to the camera, I'm going to show you here in the book that this table here shows us that the frequency of each of these fundamentals here, the frequency of these modes depends on the velocity and the wavelength. And the wavelength is given as either twice the length divided by 1, or divided by 2, divided by 3, etc., depending on what mode we are. So this is, for example, the n equals to 1 mode, n equals to 2 mode, 3, 4, 5, and then they give you this sort of generalized formula down here at the bottom. So if I wanted, for whatever reason, if I wanted the 17th mode, you could just put in n equals to 17, and it would be 17 times the original frequency. So this frequency here, if you go back one page, you'll see that that's related to the velocity, which is the square root of tension divided by mass per unit length. So that's the idea here. And if I write down those two expressions here, one is that velocity is the square root of tension over mass per unit length, and the other one is that the frequency is going to be velocity divided by 2L over n, and it's going to be like that. So in other words, that's just taking this equation here and plugging in the lambda sub n. So if I plug in 2L over n, I'll get nv over 2L. And then finally, if I plug in for the velocity n over 2L, I can multiply this by tension over mass per length. So usually we'll think of mass per length as being kind of like a number. It'll be in kilograms per meter. That's our SI units. So in other words, if you have all those pieces of information, for example, a lot of times what we're going to do is consider the fundamental mode. So often we'll set n equals to 1 because that'll be the fundamental mode, the one that controls everything else. And if we wanted higher order modes, we can figure it out from there. But so often what we'll do is we'll focus on F1, which is 1 over 2L times the square root of T over mass per length. Okay, so this is kind of our fundamental equation that we're going to be dealing with here. And anyway, that's how we'll figure out the frequency. So you can see here that I've kind of just highlighted that the F1 is just the square root of T over mu, or mass per length, and then that's divided by 2L. And then if you wanted to figure out the frequency of any of the higher modes, you just multiply by n. So just to kind of summarize that, we're talking about the fundamental string frequency given by this equation here, where this funny looking u thing, it's called mu, is the mass per length. And the frequency of any higher modes are going to be just n times the fundamental mode. And this forms a harmonic series. And so this harmonic means literally that they're multiples of the original frequency. We talked about nodes and antinodes, nodes being the place where there's not any motion happening. And the natural mode shapes are going to be those modes like n equals to 1, n equals to 2, and so on. So now we're going to have a chance to practice. So taking a look at this equation here, what do you think would happen if the string tension was increased, for example, on a guitar? Go ahead and pause here. All right, we're back. And if you have thought through this and took a look at the equation, you might see that there's a relationship between tension and frequency. If tension increases, it seems that the pitch must also increase. And if you remember, pitch is the sort of psychological sensation, right, of increases in frequency. And in this class, we consider pitch and frequency to go together. So if the frequency becomes higher, then the pitch is also becoming higher. All right. And notice that there isn't any expression so far about loudness compared with this thing. We haven't really talked about how the tension might change the loudness. It's really just the frequency that's changing here. Okay, so now if we change the length of a string by keeping the tension and the mass per length constant, what should happen to what would happen? Go ahead and pause here. Okay, we're back, and we can find that if the length increases down here at the bottom, it looks like the frequency should decrease, or the pitch should decrease. So you can see that if you made the length twice as long, the frequency should also be half as much. And so this might actually make sense that, for example, a bass, if you've ever seen a big stand-up bass, it's a very large instrument. And so, in fact, I'll just, since we're here at a computer, I will just open up a web browser and type in stand-up bass. So as you can see, it's a very large instrument, and here's a kind of an image of this here. It's just as tall as a person, and so you can see that, in fact, I'll just add this image here to the slides. Oh my gosh, that was huge. Never mind. Okay, so All right. So let's talk about the gauge of string. So we were kind of exploring each of these puzzle pieces individually. What should happen if we use a heavier gauge string? That means that you're going to make it more massive string for the same length, so more mass per unit length. But we're going to keep still the length of the string the same and the tension the same. What do you think is going to happen? All right. So if you have looked at the relationship here, you'll see that as mu gets bigger, the pitch must decrease. So anything on the bottom that's increasing, then the frequency is going to become smaller. Now you might notice, well, there's a square root type of relationship, so maybe it's not exactly in the way that you might think. So for example, if you made mu twice as much, maybe it doesn't make the frequency quite twice as much, but it'll make it 1 over square root of 2 as much. And so the square root of 2 is about 1.4. 1 over the square root of 2 is about 0.7. So in other words, it'll make the pitch about 70% as much as it was before. All right. So here's an interesting, strange-looking guitar here on the right. I'm curious, what do you think is going to increase the frequency of a guitar string more? Doubling the mass per unit length? Decreasing the mass per unit length by a factor of 2? Doubling the length or decreasing the length by a factor of 2? This is the equation that you want to use when you're trying to think through this problem. Okay, so hopefully by looking at this problem you can see that it's in fact decreasing the length by a factor of 2, which will increase the frequency by a factor of 2. And notice that if you did something like, say, oh, I don't know, increase the tension by a factor of 2, you would only get a 40% gain. And I'll see if I can convince you of that right now. Just looking at our camera here, you can see that if the frequency is 1 over 2L times the square root of T over mass per length, or mu, then you can see that if I were to say, I can also write that frequency is proportional to the square root of T. If I just want to isolate one of the variables, in fact, I could actually choose special numbers to make it so that everything else would be 1. So for example, I could make it 1 kilogram per meter, and make the L equals to 1/2 or something, so that everything else could be 1, and I could just focus on this. This is what it means proportional. It's that I'm not changing anything else, I'm just changing, in this case, just the tension. And so here you can look at this and say, well, if I were to put a 2 into here, that wouldn't be quite legal mathematically, but that would be square root of 2 times the square root of T. So I'd have to put in a square root of 2 on the other side. So I would actually multiply the original frequency by a factor of square root of 2. And as mentioned, square root of 2 is approximately equal to 1.4. Good. So in other words, increasing the tension by a factor of 2 means increasing the frequency by a factor of 1.4. So it increases it, but it doesn't increase it by like a factor of 2 just as you did the tension. Whereas on the other hand, F is proportional to 1 over the length. So that means that if L becomes multiplied by 2, this gets divided by 2. And so in other words, if the length goes up by a factor of 2, the frequency will go down also by a factor of 2. Or you could say the frequency is divided by 2 is another way you could say it. Well, maybe I'll say divided by 2. Maybe that's a good way to sort of think through it. Okay? So moving on to the next then. Next slide. I don't know how to go to the next slide. Oh, it decided to go. Okay, so let's take a look then. So just thinking about how when we have vibrating sounds, well, how does that actually change to a vibration? Like, how does that actually make like the sound that we're actually hearing? Well, this is a cool little, it's called an interferogram image, and it's talked about more in the latter part of Chapter 8. And you can see that this is a special image that shows you this very small vibrations that are happening on the actual body of the guitar after we've plucked it. And so when you pluck a string, there's a bridge, and that bridge is the connecting point to the body of the guitar. And so those vibrations of the string will then translate into vibrations of the body of the guitar. Those vibrations will ultimately then basically give you the vibrations that you're hearing. So the vibrations are not just the vibrations of the string, they're also the vibrations of the guitar body as well. And they're coupled through the bridge. This is some other just really neat interferogram images that show you the different modes that a guitar will vibrate at when you pluck different frequency strings. So sound from an acoustic guitar, and this is not with any kind of electronic pickup, is radiated primarily by, if you were just listening to the last couple of slides, you would know it's the guitar body. So it's the body that's vibrating, and that is what is producing the sounds. Okay, so let's practice some more here. If the length is of a string is L, what is the wavelength of the natural mode shown above? So this one is a little tricky because you have to count how many half wavelengths fit into the length of the string. And so here's the way that we can figure this out. If the length of the string is L, you can see that there's 5 half wavelengths that fit into here. So now you can figure out, maybe you can even write down a formula that figures out how many half wavelengths equal to the length of the string. So if I had that picture here, which I'll recreate, so 1, 2 and a half, 1, 2 and a half. If this length here is L, and it looks like this is a half of a wavelength, and this would be a full wavelength here. So there's 1, 2, 3, 4, 5 half wavelengths. So 5 half wavelengths are the length of this string. So solving for lambda, then, I can say that this is equal to 2L divided by 5. So hopefully that's one of our options here. Indeed, we see that this is, oops, well, I don't know, it didn't really show up. But here we can see that the answer is in fact D. And so you can see that the answer is this because oh, I see now. Okay, I had it just after that slide. So so the natural modes here, you can again see that n equals to 5 has 5 half wavelengths that fit in, and so therefore you can actually then figure out that the length of a wave is 2/5 L. So lastly, I'll close with a, well, I'm not going to close because I'm also going to practice a few more problems, but I've left one practice problem here at the end for you, which of the slides, which is what is the wavelength for the third harmonic of a standing wave, and there's a string that has fixed ends, and the ends are held 2.4 meters apart. So this distance here is 2.4 meters, and the length of the string is L. There's a solution on the next page, and I'm going to let you work through that one and make sure that that's making sense for you. Meanwhile, I'm going to go over a few more problems that are related to the homework in hopes of being able to help you in your quest to understand everything that is going on there. So, so we've talked about how the velocity of a wave is related to tension and mass per unit length. So in other words, the more mass per unit length, then we're going to have a lower velocity. And according to this equation that we wrote earlier, I'll bring this back up over here. If the velocity is lower, that's this thing here, then the frequency will also be lower. Okay, so maybe another way you can write that here is that frequency is equal to V over 2L for the fundamental frequency. So F1 is V over 2L, and our V we replaced with this larger thing here. So the lower the speed of the wave, then the lower the frequency that the standing wave will oscillate at. Okay. So the next thing that I'll say is maybe we should practice with some numbers here. So imagine that I had a guitar string, And imagine that we were going to, here's my sort of really crappy picture of a guitar string oscillating. It's my n equals to 1 mode, okay? So it's going to go like boing, back and forth like this, right? And so the whole string is going to go up and down like this, right? And so this is going to be my n equals to 1 mode, and my length of my string is shown here. So let's say that, for example, I wanted to have a tension on this string equals to 200 newtons, okay? And imagine that a lot of times when you order strings, they'll tell you, oh, well, the mass per unit length is equal to 2 grams per meter. Well, in order for us to be able to put things into meters per second, we need to use SI units. So 2 grams per meter is going to be 0.002 kilograms per meter. So we'll just go ahead, before we even know what we're solving for, we're just going to always try to put things into SI units. So a typical problem might ask us, for example, what is the speed of a wave on the string? That means if I were to pluck it on one side, we could ask how long it would take, but how fast would it move from one place to the other? And so we can use our formula for the speed of the wave, which is the square root of tension divided by mass per unit length. And the cool thing is here is that if we use SI units, let's see if I can get a little better focus here. There we go. If we use SI units, it'll work out to be meters per second. So here, newtons is a SI unit of force, and the mass per unit length, 0.002 kilograms per meter. This is all under the square root here. And the cool thing is that if we just plug in these numbers here, so I'm going to use 200 divided by 0.002, we get this number of 100,000. If I take the square root of this number here, of 100,000, I get 316, and so my 0.2. So we'll say that this is going to be 316.2 meters per second. So one thing I want you to notice here is that this speed is actually slower than the actual speed of sound. And so this actually gives us a hint here, is that the speed of a wave on a string doesn't necessarily have to be the same as the speed of sound. And this is an important point that I want to draw out. I'm going to actually bring up one of the simulations that we've done before. And I'm going to do no end. And remember that if we were doing this thing here where we were moving and watching the speed of the wave. And so you remember that the speed of the wave has nothing to do with whether it's a slow wave, a low frequency wave, or a high frequency wave, that it's still the same speed no matter what, right? That's one thing you know. But the other thing that's interesting is that the speed of this wave is not going to necessarily be the speed of sound. So in the case where I have a fixed end, and I'm doing some kind of oscillations here, and making some standing waves. In fact, maybe I'll do some kind of oscillation here, and if I change the frequency just right, you can maybe find that I'll get some standing wave. Maybe, I don't know. Let's see if I can find it. There we go. If you find just the right frequency, you can get it to go standing wave. So this is pretty close to being a standing wave here. I'd have to mess around with it a little bit more to get the right. Wow, it's going crazy. So in other words, okay, it's probably not, I'm probably not going to just arrive on it by accident here. I have to spend a little more time with it. But the point was that I wanted to make is that the speed of the wave, then this transverse wave, does not necessarily need to be the same thing as the speed of the sound wave. And so, but what will happen is that as we create standing waves, we will actually see that we're creating a frequency of oscillation, and that frequency will be the same frequency as the sound wave that's produced. So let's continue on with this example here. I've got the problem was basically that I've got a guitar string, and we pluck it. And then the question is, like, what happens? Well, one of the things that happens is that that the wave has some velocity. So it's going to go there and back and there and back. And if we wanted to, we could use this velocity and the length, and we could figure out how long does it take to go there and bounce back and so on. But the other thing that we could be interested in now is to think about what is the frequency of our lowest frequency mode, so our fundamental mode. And as you know, this F1 is equal to V over 2L, right? And we did this 2L because the half of a wavelength fits into the space here. So if we were to continue this onward, I guess I'll just give myself a little extra paper here. If I were to continue this onward, like this, you could actually see that this is 1/2 of a wavelength here. And then this would be another half of a wavelength here. Oops, 1/2 of a wavelength. So in other words, half of a wavelength fits into this length here. So that means lambda is equal to L times 2. So that's how we kind of get that idea. That's why this frequency is usually V over lambda, but lambda is 2L, or 2L, right? So that's how we're getting that sort of connection between those two ideas here. So our fundamental frequency, nonetheless, is going to be V over 2L, and I can take a look at this here and say, well, F1 is going to be the speed, which is in this case 316.2 meters per second, as we found above, divided by 2 times the length of the string. Now, a typical guitar has a length of somewhere around 0.8 meters. So I'm going to say 2 times 0.8 meters. Plugging in the numbers, I'm going to find that this is 316.2 divided by 2 times 0.8. And I get 197.6 hertz. And so how did I know it's hertz? Because I could make some horrible pun here because it really hurts to do math, haha. And this is going to be meters per second divided by meters, and it's 197.6. And I have meters canceling with meters, and then 1 over seconds, which I can identify as being hertz. So in other words, this is the tone that is going to be produced. And so looking at that, we now are empowered to figure out for any situation, if we were given the length of the string, if we were given the tension and the mass per unit length, we would be able to figure out what the fundamental frequency is. The next thing that I might ask is, well, could we figure out what the second harmonic is? Could we figure out what the third harmonic is? Those kinds of questions. And yes, we can answer all those questions now because we now know what the fundamental frequency is. Okay, so moving along, we could ask, well, what is the second harmonic of this thing? Well, we could just open up my calculator here, and I could say, well, 2 times this answer is my second harmonic. So I could say my second harmonic is 395. I could also ask, well, what is my third harmonic? Well, my third harmonic is going to be 2 times, third harmonic is going to be 3 times 197.6, which is going to be 592 hertz, right? And so on and so on and so on. We can just figure out any of the harmonics just based on multiplying. And you could always redo the calculations, or if you just figure out the fundamental, you can redo the calculation each time, given the equations here in your text, which is that your frequency is V over lambda, but your lambda is different depending on what your mode is. You could always do that, or if you figured out the frequency of your fundamental and the only thing that's changing is the mode number, then you can just multiply by n by your mode number. So, okay, moving along, I'll try a few more examples here. Let's take a look at, so I want to show you how people try to decide mass per unit length to use for like a guitar string or a bass string or something like that. So imagine that we had to tune a string to an A, which an A4 is, I believe, around 440. So the tone A is going to be a 440 hertz signal. Okay. So suppose that we wanted to figure out what kind of mass per unit length to use. So we're going to tune our string to this. And then the deal is, though, is that we know that from doing lots of testing that when we're making our guitars, that if we have a tension beyond 300 newtons, then we're really in bad shape. That's like 10 kilograms, or in other words, about, no, sorry, 300 newtons would be about 30 kilograms, or about 60 pounds worth of force pushing on it. And so we say, okay, well, we don't want to have that much tension on our strings, because it ends up, let's say, breaking the wood, or there's something not so good that happens. So we're going to limit our tension to be 200 newtons. Okay, we'll just say that in our problem. So we say, oh, 300 is the limit. Let's dial it down a notch and say, okay, 200 newtons is going to be the tension that I want to go for. And I have this frequency here that I want. That's meaning we have a fundamental frequency. And the question is, okay, and then let's just say that our guitar, let's just say that the length of our guitar is 0.8 meters, or that could be 80 centimeters, or it could be 800 millimeters. All those things are the same thing. So I want you to also just make sure that you can remember how to do those kinds of conversions. And so if I want the tension to be 200 newtons, what kind of mass per length do I need? Well, in order to solve this kind of problem, we need to take a look at what our relevant formulas are. So one of them is going to be that the velocity is going to be the square root of tension divided by mass per unit length. So if you notice here, we can actually rearrange this equation to solve for mass per unit length. So imagine that we'll, in our next step, we're going to figure out what the speed needs to be. But let's kind of set ourselves up here. If I took this equation and I squared both sides, I would get v squared is t divided by mass per length. If I multiply both sides by mass per unit length, I would get v squared times mass per length equals to tension. And finally, if I divided both sides by v squared, I would get that the mass per length is equal to t divided by v squared. So this is going to be one of the equations that we're going to use to try and figure out what our mass per unit length should be. Now the catch is that we were given the tension, but we were not given what the velocity should be. So let's go there next. The equation in chapter 8 says that our fundamental frequency is going to be v divided by 2 times the length. So if that's true, I need to rearrange this here to solve for v. Fortunately, that's just multiplying both sides by 2l, 2l and 2l, and those cancel out. And v is going to then be 2 times l times f1. Cool. Now we're actually in a place where we have the length, which is in SI units is 0.8 meters. Keep in mind, if you were given it in centimeters or millimeters, you'd need to convert to meters. And we are given also what frequency we're shooting for this string. So 2 times 0.8 times 440 is going to give us our speed. And if you notice here, this is meters, this is 1 over second, so it is going to be meters over seconds. And when we put these numbers all together, I'm going to get out my calculator again, and we're going to do 2 times 0.8 times 440, and we're going to get 704 meters per second. Now notice here actually that this speed is actually faster than the speed of sound, and that's okay. It's the speed of the wave on the string. So imagine that this, you know, just like the demos that we've done where a person is kind of holding onto a string and they make some bump, and then maybe this other person is kind of holding onto it, trying to hold it steady. This bump is going to move, right? The transverse wave is going to move at 704 meters per second. That's the picture that I have in my mind, okay? So now we have everything that we need. This equation here, we can plug in 200 newtons, and we can plug in 704 meters per second. We have to square that. And it turns out, and I don't require that you know how to reprogram these units, as long as you know that what you need is SI units. And if you put newtons on the top, meters per second on the bottom, then the units of your mass per length, they're going to be kilograms per meter. So mass per unit length units is going to be kilograms per meter. Okay, I'll write that up there just to remind us. So I understand that there's an M and an M. Hopefully you know that what I mean is that this is mass kilograms, length meters. So sometimes we'll write a little bracket around to indicate that we mean the units here, like this. All right, good. Finally, I'm going to plug in the right numbers into here, and checking those numbers, we're going to say 200 divided by 704 squared is going to give me this tiny, tiny number. Okay, let's take a look at that tiny, tiny number. So that's going to be, I'm going to write it down here, 0.0004, and then I'm going to just say 03, just so we don't chop off all the digits. Obviously, we don't need that many digits. That seems like a little ridiculous. It says automatic. Well, something like this, but okay. I'm trying to maybe make it in a format this is the format that I usually use, is engineering format. Well, I usually use this format here, where it says 403 times 10 to the minus 6. I would just like for you to be able to make sense of the results, so whatever way is best for you. Looking at this, our unit here is kilograms per meter. This is my mass per length, okay? So mass per length is 0.00043 kilograms per meter. That's the same thing as 0.403. So sliding this over 3 decimal places will change me from kilograms to grams. So 0.403 grams per meter. That means that if you had 1 meter of this string, it would only weigh less than half a gram. And if you had 2 meters, it would be about 0.8 grams. So this is the kind of mass per unit length that's actually very typical for musical strings, for an instrument. So maybe you know this if you've ordered guitar strings online or something like this, then you've seen this kind of thing happen. So there's a few problems to help you get used to these calculations here, but the key features are we solved for the mass per unit length in terms of tension and velocity, and we also used our fundamental frequency equation, which is V over 2L. So these are the two equations that we used and we rearranged in order to solve for the mass per unit length. So we combined those together. All right, very good. And I guess you could also combine them algebraically ahead of time if you'd like to. And in that case, we would have T divided by 2LF all squared. And that also would give you your correct result. Okay. So now, maybe the last kind of comments that I want to make are just simply around what to do if you wanted to change the frequency, for example. So this, going back to this kind of proportionality discussion here, is that imagine that you had a string, and we just did this string, and we figured out, okay, this is the mass per unit length that you need to get this string to be at 440 hertz. And what if I wanted to go up an octave? Well, you could redo all the same calculations, or what you could do is just say to yourself, well, what I want here is I want my F1, which is 1 over 2L times the square root of T over mass per length. I want to do something to let's say I want to do something to the tension to make this frequency be twice as much. Well, you could say, well, don't you just like multiply by 2 on the tension here? Well, if you did that, you'd be multiplying by square root of 2 here to keep this equation being still true. So, in other words, T multiplies by 2 means that frequency multiplies by the square root of 2, or in other words, frequency multiplies by about 1.4. So that's not actually going to do it. If I put in a 4 here instead, then I'd have a square root of 4 here, and the square root of 4 is 2. So in other words, if I multiply t by 4, then the frequency would get multiplied by the square root of 4. In other words, the frequency gets multiplied by the square root of 2. So that's interesting. What if I wanted to change the mass per unit length? If I double, so because that's kind of looking messy now, we're going to go to a new example, which is, here's my original equation. F1 is 1 over 2L, square root of t over mass per length. And what if I doubled the mass per length? Well, if I did that, if I put a 2 in here, that would be like dividing by square root of 2 over here. Do you see that? If I wanted to multiply by, so in other words, taking mass per unit length and multiplying by 2 means take the frequency and divide by square root of 2. Similarly, I want to try to write a little neater this time. 1 over 2L times the square root of t divided by mass per length. If I multiplied mass per length by 4, that would be like multiplying 1 over square root of 4 over here. You can see there's a 1 over square root of 4. This is equal to 1 over 2L times 1 over square root of 4 times the t over mass per length square root. So in other words, just remember that if you had the square root of a times b, that's equal to the square root of a times the square root of b. If you're not remembering that quite clearly, you might check out the math review that's on Blackboard. So anyway, if the mass per length becomes 4 times as much, that means that the frequency is going to be divided by the square root of 4, which is divided by 2. So interestingly, if you wanted to go up an octave, if you wanted to go down an octave, you would make the mass heavier by a factor of 4. If you wanted to go down 2 octaves, you'd make the string heavier by a factor of not just 4, but 16, because the square root of 16 is 4. And remember that every time you go up an octave, that means to take the frequency and multiply by 2. And so if you multiply by 2 twice, it's going to be going up 2 octaves. If you divide by 2, that's going to be going down an octave. Okay? So, all right, hopefully that's helpful for you, and it's kind of falling in line with the homework. And I think that's most of the things that I wanted to talk about. So we talked about proportionality, we solved a few problems, and another thing that I just wanted to mention here is that when we are looking at the oscillations here, for example, let's just even take a look at this one, the third harmonic here. At this location right here at the node, if we put a pickup right there, you actually would not hear things very well. Instead, the pickup should be closer to the places where the wave is actually vibrating. So for example, over here, if you put a pickup right in the center of the string for the n equals to 2 mode and you plucked it, then you wouldn't actually pick up very much fluctuations in amplitude. So that's just something to consider as you're thinking through things. And again, some summary points that I think are commonly mistaken here is that when we talk about the speed, for example, of this wave, and I'll bring us back to an equation that reminds us of what the speed is. Let's see, speed of wave, where's my speed? Our speed is going to be this mass per, our speed is going to be this square root of tension per mu. In fact, I should probably maybe just add this into the slides here. But this is going to be our speed. I'll go ahead and put that in here. So there we go. So our speed is going to be tension divided by mass per length, and so as we put these together here, we can actually we see that the speed of the wave on the string is not the same as the speed of a sound wave, which is what we've been used to doing. And one of the consequences of being able to vibrate the string in different ways is that we can actually see that there are many different natural modes of a string, each of which produce different frequencies. And finally, we also talked about how there can be many frequencies present with each other, and these will add to the unique qualities of the sound, which is also known as the timbre. And that was discussed here when we looked at the spectrogram of the birdie, and also when we did this the simulation of this Fourier synthesis. By the way, this is Joseph Fourier, who actually had discovered about how any kind of waveform was able to be separated out into the sum of all these different sinusoidal wave components, much like how if you wanted to make a nice cake, you could dissolve the cake in a lot of chemicals maybe and somehow find out what all the different ingredients were. So basically you can think of this as being all the ingredients together telling you what kind of wave you created. So yeah, I think that's most of the info that's needed for this homework, and hopefully this is helping you to put together the story as you're continuing. Please remember to watch this short video about standing waves, and it'll help also give you a visual. Thank you for your attention.